One of the other nice things that integration by parts gives us the ability to do is to handle certain integral formulas that turn up from time to time in calculus. In this particular case, we're talking about formulas that involve sine and cosine and powers of x. And this is actually sort of a generalized way of looking at how would we handle a formula that involved x raised to some real number power n times the cosine of x dx. In the in the integration by parts rule, the integral of u dv is equal to uv minus the integral of v du. We have to identify what do we want to have our function u equal, and what will our function n equal, dv equal, pardon me. Well, in this case, it turns out when you have a trigonometric function involved in your integral, a good plan is typically to start with dv being that trigonometric function, especially if it's one that we can integrate relatively easily. So that means we're going to take u equal to x to the n. And the reason why we want to do that is we want to see if there's a way to break this down. And we might notice this little structure over here, n, and then we have x to the n minus 1. And we've seen that when we've taken a derivative using our general power rule for derivatives. That is, if we have x raised to the power n, where n is not equal to 0, then we get n times x to the n minus 1 power dx in our differential notation. As far as our trigonometric function is concerned, the integral of cosine of x is the sine of x. That's our antiderivative. And so putting together this formula, we see that by using our integration formula, the integral of x to the nth power times the cosine of x dx should be exactly the same as by our formula u times v. So we've got x to the n times our function v sine of x minus the integral of v times du. And for v, we have sine of x. And of course, for du, we have n times x to the n minus 1 dx. Well, sure enough, that's our formula as displayed above. When we simplify, we would have x to the nth power times the sine of x minus n, which is a constant, times the integral of x to the n minus 1 power times the sine of x dx, which is the formula that we were looking for. Now, the usefulness of this particular formula, sine of x dx, let's try that. There we go. The beauty of this kind of formula is that we can use it whenever we are in a situation where we have an integral that looks like this one and we can break it down. There's a similar one for sine of x, by the way, but let's just take a simple situation where we have n being a power greater than 0, right? And let's say it's an integer. So let's say that we use integral of x to the first cosine of x dx. Well, by this formula then, our integral is going to be x to the first times the sine of x minus the antiderivative of 1 times x to the 0, which is 1 sine of x dx. And we can see that what we're going to get right here is going to look like x times the sine of x minus the negative of cosine of x, right? Don't forget our antiderivative of sine of x is actually the opposite in sign of what we would expect. So we're going to end up with a function that looks like x sine of x plus the cosine of x plus c. So we're done. That's a pretty good little rule to have.